How does ships float? A ship that floating on water is subjected to two types of forces. The two forces are the gravity and the buoyant force. As we know, gravity is a force that attracts objects toward the center of the earth. In the case of a ship, the gravity pulls the ships downward into the water. Buoyant force, on the other hand, is an upward force exerted by a fluid that opposes the ship weight. Therefore, we can conclude that a ship floats because of the balance between the gravity force and a buoyant force. The Archimedes Principle states that any object completely or partially submerged in a fluid is buoyed up by a force with magnitude equal to the weight of the fluid displaced by the object. Actually, this statement can be extracted into several components. In the first statement here, any object completely or partially submerged in a fluid, this part of the statements apply to any object regardless of its shapes, size or density, and as long as it is placed in a fluid. And while in fluid, the object can be either completely submerged like a stone in a water or partially submerged like a boat floating on water. The second statement is buoyed up by a force. This statement means that when an object is in a fluid, it experiences an upward force. This force is what we commonly refer to as a buoyancy force. The buoyant force is the reason why objects feel lighter when submerged in water, or why some objects like boats float. And the statement with magnitude equal to the weight of the fluid displaced by the object, according to the Archimedes Principle, the force exerted upward on the object, or the buoyant force, is exactly equal to the weight of the fluid that the object displaces. When an object is submerged in a fluid, it experiences an upward force known as the buoyant force. We can denote buoyant force as Fb. The Fb can be calculated by multiplying the volume of the displaced fluid, the fluid density, and the acceleration due to gravity. Let's discuss how to derive this equation. The buoyant force arises due to the difference in pressure between the top and the bottom surface of the submerged object. This pressure difference is denoted as delta P equal to P2 minus P1, where P2 is the pressure at the bottom surface and P1 is the pressure at the top surface. We can rearrange the equations as the factor of Fb, which yield Fb equal to A bracket P2 minus P1. We also know that pressure in a fluid at a certain depth can be expressed as P equal to rho hg, where rho is the density of the fluid, h is the depth of the fluid, and g is the acceleration due to gravity. Therefore, the buoyant force can be expressed in terms of the fluid density and the acceleration due to gravity and height difference. In these formulations, h2 is the depth at the bottom surface and h1 is the depth on the top surface. The volume of the fluid displaced by the object is equal to the volume of the object submerged in the fluid. Therefore, we can express Vf equal to A bracket h2 minus h1. And substituting the expressions for the volume of fluid displaced Vf into the buoyant force, we should get the final expression as shown here. These equations indicate that the buoyant force is equal to the weight of the fluid displaced by the submerged object. In these equations, rho f represents the density of the fluid, g is the acceleration due to gravity, and Vf is the volume of the fluid displaced.